In this module, we will learn about stoichiometry and stoichiometric calculations. We know that chemical reactions can be illustrated through a chemical equation. A chemical equation can be divided into two parts. The reactants appear on the left side of the equation. In this reaction, hydrogen and oxygen are reactants. The products appear on the right side of the equation. In this example, water is the product. We've learnt that the law of conservation of mass states that in all chemical reactions, the total mass of the reactants is equal to the total mass of the products. This means that the equation of a chemical reaction should be balanced. Notice that the equation for water is balanced. The number of atoms on the left side is equal to the number of atoms on the right side. A chemical equation in which the number of atoms of each element is equal on the reactant side and the product side is called a balanced chemical equation. Let's look at the steps to balance a chemical equation. Let's say we have to write the balanced equation for the combustion of propane. The first step is to write the chemical formula for the reactants and products. In this case, propane, that is C3H8, reacts with dioxygen, O2, to form carbon dioxide, CO2, and water, H2O. Note that there are 3 carbon atoms, 8 hydrogen atoms and 2 oxygen atoms on the left side, while there is 1 carbon atom, 2 hydrogen atoms and 3 oxygen atoms on the right side. Next, we have to balance the number of atoms of each element one by one. Let's begin with carbon. There are 3 atoms on the left side and 1 atom on the right side. So, we will multiply CO2 by 3. This means that 3 carbon dioxide molecules will give us 3 carbon atoms. Now let's work on the hydrogen atoms. There are 8 atoms on the left side and 2 on the right side. So, we can multiply H2O by 4. This means that 4 molecules of water will give us 8 hydrogen atoms. Now, let's look at the oxygen atoms. There are 2 oxygen atoms on the left and 10 on the right side. 3 multiplied by 2 oxygen atoms, that is, 6 oxygen atoms in carbon dioxide, and 4 multiplied by 1, that is 4 oxygen atoms in water. 6 plus 4 gives a total of 10 oxygen atoms on the right side. Hence, we will multiply O2 on the left side by 5. Finally, verify that the number of atoms in each element is balanced. In this case, we have equal number of atoms on both sides. Hence, this is a balanced chemical equation. A balanced equation helps determine the quantitative relationship between the reactants and products in terms of number of moles, molecules, atomic masses, and volumes. For example, according to this balanced chemical reaction, 1 molecule of propane gas reacts with 5 molecules of dioxygen gas to give 3 molecules of carbon dioxide and 4 molecules of water. And 1 mole of propane gas reacts with 5 moles of dioxygen gas to give 3 moles of carbon dioxide gas and 4 moles of water. Similarly, 44.09 atomic mass unit of propane gas reacts with 160 atomic mass unit of dioxygen to give 132.03 atomic mass unit of carbon dioxide and 72.06 atomic mass unit of water, and 44.09 gram of propane gas reacts with 160 gram of dioxygen to give 132.03 gram of carbon dioxide and 72.06 gram of water. And the total mass of the reactants, that is 204.9 grams, is equal to the total mass of the products, which is also 204.9 gram. The calculation of quantitative relationships of the reactants and products in a balanced chemical reaction is known as stoichiometry. The coefficients in a balanced chemical equation are called stoichiometric coefficients. Stoichiometric calculations help understand the mass and mass relationship. This means that if we know the mass of one of the reactants or products, we can determine the mass of the other reactants and products. Similarly, it helps understand mass and volume relationship. That is, if we know the mass or volume of one reactant or product, then we can calculate the mass or volume of the other reactants or products. And if we know the volume of one reactant or product, then we can calculate the volume of the other reactants or products. Most chemical reactions take place in solutions. Hence, we need to understand how to apply stoichiometry to reactions in solutions. For solutions, we need to know the concentration, that is, the number of moles present in a certain volume of solution. We can express the concentration of a solution present in a given volume through four methods. They are mass percent, mole fraction, molarity, and molality. Let's look at each method. The mass percent of a solution is determined by dividing the mass of the solute by the mass of the solution and multiplying it by 100. For example, let's say a solution is prepared by adding 4 grams of substance A to 20 grams of water. We need to find the mass percent of the solute. Based on the mass percent formula, we need to divide the mass of A by the mass of the solution. That is, mass of A plus the mass of water. After performing the mathematical calculation, we get the mass percent of A as 16.66. Now, let's look at mole fraction. Mole fraction is the ratio of number of moles of a particular component to the total number of moles of the solution. Mole fraction is a way to express the composition of mixture. For example, if a substance A dissolves in substance B, and their number of moles are Na and Nb respectively, then the mole fraction of A will be the number of moles of A divided by the number of moles of solution, and the mole fraction of B will be the number of moles of B divided by the number of moles of solution. Let's say we have to find the mole fractions of water and glycerol. When 92 gram glycerol is mixed with 90 gram water, given that the molecular weight of water is 18 gram and the molecular weight of glycerol is 92 gram. To apply the mole fraction formula, we first need to find the number of moles in water and glycerol. The number of moles of water is 5 and the number of moles of glycerol is 1. We then add them to obtain the total number of moles in the solution. From the calculation, we get the total number of moles in the solution as 6. Then, we find the mole fraction as per the formula. We get the mole fraction of water as 0.833 and the mole fraction of glycerol as 0.167. Next, let's look at molarity. Molarity is the number of moles of solute in 1 liter of solution. It is represented as capital M. Let's say we have to find the molarity of a solution formed when water is added to 11 gram calcium chloride to make 100 ml of solution. To find the number of moles of a solute, we need to divide the mass of calcium chloride by the molar mass of calcium chloride and need to convert 100 milliliter solution into liter. By applying the formula for molarity, we get the molarity of the solutions as 1.0 m. Finally, let's look at molality. Molality is defined as the number of moles of a solute present in 1 kilogram of solvent, and it is denoted as lowercase m. Let's say we have to find the molality of a solution of 10 gram sodium hydroxide in 500 gram water. To find the number of moles of solute, we need to divide the mass of sodium hydroxide by the molar mass of sodium hydroxide. We also need to convert 500 gram water into kilogram. Thus, after applying the formula, we get the molality of the solution as 0.50 m. At times, when reactions occur, the reactants are not present in the amount required by the balanced chemical equation. Let's understand this concept through a real-life example. For example, let's say that 2 slices of bread and 1 slice of cheese makes 1 sandwich. Now, if we had a packet of bread with 10 slices and a packet of cheese with 6 slices, how many sandwiches can we make? The answer is 5 sandwiches. In this example, bread is present in lesser amount and gets fully consumed, and hence we cannot make any more sandwiches, although 1 slice of cheese is left. Thus, bread is known as a limiting reagent, as its shortfall prevents us from making any more sandwiches, while cheese is the reactant in excess. Let's look at the steps to find a limiting reagent and reactant in excess in a chemical reaction. Let's understand how to calculate limiting reagents from this example. Assume that we mix 50 kg of nitrogen gas and 10 kg of hydrogen gas to produce ammonia gas. Here, we have to determine the limiting reagent during the production of ammonia. First, we have to write the balanced chemical equation of the reaction. Next, we have to convert the given amount into moles. First, we'll convert the mass of nitrogen into grams and then apply the formula to find the moles, which is 1785.7. Similarly, we'll convert the mass of hydrogen to gram and then apply the formula. We get the moles of hydrogen as 4960.3. From the balanced chemical equation, we can conclude that 1 mole of nitrogen reacts with 3 moles of hydrogen. Thus, 1785.7 mole of nitrogen reacts with 5357.1 moles of hydrogen. However, we have 4960.3 moles of hydrogen, not 5357.1 moles. Thus, we can conclude that nitrogen is not the limiting agent. If we test in the reverse manner, that is, 3 moles of hydrogen reacts with 1 mole of nitrogen, we get 1653.4 moles of nitrogen, as against the 1785.7 moles of nitrogen. Thus, we can say that nitrogen is the excess reagent, while hydrogen is the limiting reagent. You have now reached the end of this module. In this module, you have learnt that a chemical equation in which the number of atoms of each element is equal on the reactant side and the product side is called a balanced chemical equation. The steps to balance a chemical equation are: write the chemical formula for the reactants and products. Balance the number of atoms of each element one by one, and verify that the number of atoms in each element is balanced. A balanced equation helps determine the quantitative relationship between the reactants and products in terms of number of moles, molecules, atomic masses, and volumes. The calculation of quantitative relationships of the reactants and products in a balanced chemical reaction is known as stoichiometry. The coefficients in a balanced chemical equation are called stoichiometric coefficients. The mass percent of a solution is determined by dividing the mass of the solute by the mass of the solution and multiplying it by 100. Mole fraction is the ratio of number of moles of a particular component to the total number of moles of the solution. Molarity M is defined as the number of moles of solute in 1 liter of solution. Molality M is defined as the number of moles of a solute present in 1 kg of solvent.